Let's do logistics and questions right off the bat. So you guys have questions for me or any kind of logistical type stuff to go over? Couple things from my end. The quiz will be out a little bit later tonight. I didn't have a chance to type it up this afternoon. Expect that about an hour after class, if it even takes me that long. So quiz will be out just a touch later than it normally is today. Homework is obviously out. Start working on that sooner than later. There are some errors in there that you guys will not necessarily know how to deal with yet. Depending on how much you guys went over kind of troubleshooting in class on Monday, it'll take some getting used to. So like get on Piazza, ask questions about what those errors mean early, because that'll kind of require us to answer those questions, right? That being said, if you're really principled about laying out your cases and split cases one at a time, you don't try and lay out too many things at once or kind of get ahead of yourself. It should be pretty straightforward. Other stuff. Homework 2 should go out tomorrow after class. That'll be due sometime early next week. And I can't think of anything else off the top of my head. We probably have a slightly shorter lecture today. Don't hold me to that though. I have a tendency to talk a lot. So we'll see if that actually is shorter. Otherwise, any other questions before we get rolling today? Going once, twice. You're teasing me with that hand. Like it's kind of held up. It's not quite though. Oh, Linnea, thank you for bringing that up again. You guys still can't submit homework 1. I forgot to open that up yesterday. I will do that. If I give you guys some time to do a problem today, I'll probably go and do that while we're sitting here. So thank you for that reminder, Linnea. That completely slipped my mind. Cool. Otherwise, let's jump into it. So yesterday, we took a look at an evaluation. I believe it was of what function did we evaluate by hand yesterday? I've already forgotten. Was it tail and head that we did that for? And I think we did plus a few days ago, right? Oh, and sum was, yeah, that was it. Okay, so let's revisit the sum function. I want us to take another look at that. So we defined sum like this. Sum took a list of natural numbers and it returns a natural number, the sum of all those numbers. The sum of nil was 0. And the sum of cons, x's, was plus x sum x, or sorry, not x's, just x's. Sum x's. Does that look familiar to everybody? When we evaluated this, I'm going to go and grab that because that took longer to write. Okay, I don't like writing like this either. We're going the other way. Sweet. Okay. That was this one. Perfect. We had this long evaluation, right? Was there anything wrong with this? It's kind of a big pain in the butt, right? How we had to kind of say, I need to do plus on all this stuff, but I couldn't reduce it as we went along, right? There wasn't any way for me to like, oh, what just happened there? I haven't seen that before. Weird. Folks online, you can still Can you guys hear all right?
Yeah, now we can hear you.
Okay, cool. I was trying to fix something and turn my Wi-Fi off. Looks like I have to restart the Note app. It didn't like something I did. Okay, anyway, there was that big long execution where we had, I'm just gonna do it by hand and not risk that again. For something like sum 1, 2, 3, we'd have a whole bunch of partial evaluations. So we did kind of, first off, we had a cons case. So it was sum, or rather we had plus, and here we had 1, and then sum 2, 3, which was then equal to plus 1 plus 2, sum 3, like that, and so on. The way we evaluated this and wrote this down is kind of inefficient. Can anyone point out for me the inefficiency here, how we can maybe clean this evaluation up as we go along?
You could pre-compute sums before you're finished with the expansion.
Right on. Is I can kind of like collapse all these numbers into a single like sum so far, right? I don't need to like keep track of, oh, and add this, and add this, and add this, right? So in this step, this is just plus 3, right? I can keep track of the sum as we go. I don't need to just kind of create this big stack of stuff to do. As we would imagine, and this will come up sometimes when you're programming in Scala, you'll hit a limit of your stack size and you'll get a stack overflow. This is what gives you a stack overflow, something like this, is when you have this recursion that's happening that creates a giant call stack where you have like a bunch of plus. So say I did this sum, but on like a list of 10,000 numbers, it would be a big call stack, right? So like, so how can we get this better? Well, we can add them together as we go. But does my current definition of sum do that? Not really. Can it do that? I don't know. Not maybe in its current form. So we might revisit the way we define sum. Let me look at my notes real quick, see where I should go next. Let's try and redefine this in a little bit of a different style. And to do this, we're going to define a new function. And this new function is going to help us basically do this addition as we go along. And we'll use this to kind of piecemeal, start to add up these sums and keep that call stack basically down to one single call at any given point. So I'll mostly write this one down for you guys. We'll do this in a little bit different. So I'm going to introduce something called an accumulator. This accumulator will capture the value of a computation so far, right? Or some kind of partial computation. It's not quite when we're done, but like it's somewhere, some step along the way is the idea here. Now, how are we going to do this? It's going to require us to change the type of our function right off the bat. It's going to have to just be a little bit different. We're not going to be a list of n to n anymore. Instead, we're going to have a value that we pass into this function that is that so far value. It's like, what have I computed up to this point? So For sum, what is that computation going to be? What's the value that's kind of intermediate that we carry along with us? The sum so far, what type should that be? Any ideas?
It's just going to be a natural number, isn't it?
Right on, just a nat. And so instead of having a list of n to n, we'll have a list of n that takes another n and outputs an n. Okay. This is kind of a rephrasing of the same problem, except now we can kind of give it an accumulator value up front. So this is the accumulator. So now when we go to define this function, I'm going to write out some similar cases to start us off. And there will be a bit of a departure. We're going to do some stuff a little bit different this time. We'll call the accumulator ACC, nice shorthand, 3 letters. But we need to fill in these holes. So I'm going to ask you guys semantically as a question, just for us to talk about. If I am summing up numbers, I have an accumulator that was the rest of the list I added up. And I don't have any list left. I'm in this empty list case. I don't have any more list. What's the sum? So the sum of a list where I'm giving you the values so far, and we get to the empty case. Right, so it's gonna be just the accumulator value. So instead of putting 0 here, we're putting ACC. Okay, so our output's gonna be ACC. Now how about for the cons case? Thoughts on the cons case? I'll give you a hint. It's not going to change. Well, it's going to change a bit, but not a ton. It's going to resemble the other one.
But like an add function in it. So I guess we do then the sum of the constructor of the accumulator and x, and then x's.
So sum of, say that again.
Sum of then you add the accumulator and x.
I'm just going to use the symbol plus this time.
And then the other parameter to that, the other argument to that would be x's.
Okay. What do we think about that? A lot of you are probably really confused. How could we tell if this is correct, though? We could start writing it out, do an evaluation by hand, right on. So let's do just that. So let's do sum of 1, 2, 3 again. So sum of 1, 2, 3. This is a cons case, right? So it's like cons 1 and then 2 and 3, right? So 1 is our x. Oh, wait. What error did I just make here? How many arguments does sum take now?
Well, I mean, it should take 2.
It takes 2, but I only wrote it with 1. What should our kind of initial value be here? What else do I need to give it?
0.
Why is 0?
The accumulator won't start out at 0, probably.
Right. So you want your accumulator to probably start at 0. That makes sense. Now we can actually do the evaluation. So which case do I match to? I match the cons case. And when I have cons here, it says replace cons with sum of ACC. Here, ACC is 0 plus the head of the list, X, which is 1 from here. And then X's. Here, X's is 2 and 3. Everyone following along with that first step? If you're not, please say something now and we can talk about how we got there. Yes.
Oh, wait, so, is, I'm confused, oh, never mind.
Good, cool. So, and of course we can reduce this right away to sum of 1, 2, and the list 2, 3, right? Okay, so now we can do this one. This is another cons case. This time we do sum of ACC plus X, so 1 plus 2. And then X's, which is the list of 3. Okay, or I could write that in another way as cons of 3 and nil. Okay, I can collapse that 1 and 2 together. You guys probably are catching on how this works now. So it's 3 with cons of 3 and nil. Still following? Everyone's with me? Cool. Last case. Which case do I hit in my sum definition here? Is it cons or nil? Still cons, right? The outer constructor here is still cons. And I replace it again with sum of ACC, which is 3, plus here it's 3. And then replace that with nil, okay? I do my reduction. I get sum of 6 and nil. We go and look at our case for nil, which says just output ACC. And ACC here is 6. Now that wasn't that bad, right? It still took 6 lines. It's going to take the same number of lines of code or same number of executions at the end of the day, but it's not creating this big giant stack. And remember, this was just one step of the stack. We could go back to the notes yesterday, and it was this big, kind of nasty call stack that we just don't want to deal with. And also note that here, I also did the reduction step for the sum at each place. Normally that'd just be a quick, like just add the things together. Here, so we could, for instance, remove that line, remove that line, remove that line. So now we've done this evaluation in 3 lines of code, same number of kind of steps of execution, but much reduction in the space component, right? Or space savings are there. Yeah, so there's a question, why does the interpreter implement a stack rather than optimize to use a single sum register? I would be lying if I said I knew how the Scala compiler works. And I believe that the compiler will do a lot more optimization. We're using an interpreter, and the interpreter does not do any kind of optimization on your recursions on its own. The compiler will. So sometimes compilers will actually make this conversion for us. A lot of the times when you write bad code, sometimes the compilers clean them up for you. And in this case, with the interpreter we use in Scala, we can't get away with that. We have to do it this way. And there's actually a really good reason to do this anyway. Because if we think about it, the sum function's a little restrictive, right? Is I can't give it, say, a starting value. And I might want to. There might be a very good use case for doing that. Say, I want to take the sum of a list, but have the starting value be 10. Seems kind of silly because you could just add that to the list and add it together that way, but it's still something you might want to do. And maybe not even with some, maybe some other function has a similar story, right? Sweet. So yeah, the takeaway here, it's a much cleaner call stack. Which is also going to be much faster because you don't have to deal with all those space kind of manipulations of state space and stuff. Your memory is going to be much more tight, much more controlled. You're going to have a smaller program because of that. Is there another function that we could maybe do a conversion like this to? Or maybe a function that we wrote that didn't have an accumulator in it necessarily, but sort of did? Oh, go ahead.
You do length.
We could do length. Could we do length? Can we do length? We might be able to do length. Yeah, I guess we could do length, I think. Let's do it. Let's do it by hand. Not what I had in mind, but let's do it. Trying to think about that one now. Length. So actually, length has an interesting, almost anti-pattern going on here, but let's do it because this is going to be, I think, a good walkthrough anyway. I like this. And Brian, to answer your question, we'll get back to the function I had in mind. So the length function we originally defined like this. We had length of a list of A to a nat, length of nil is 0. Length of cons x's is equal to s of length x's. Now my question for you is, if we did an execution of this, does this have the same problem of the call stack getting really big? Yeah, but does the S actually have any kind of computation associated with it? Not really. Not really. So it's like that S isn't, we're not waiting for S to do anything. So it's not going to save us any time, but we could make the same transformation and make this an accumulator, put it into what we call accumulator passing style, which is a word I was putting off till now. So we have APS, which is what we're doing here, which is accumulator passing style. And this is where we pass an accumulator with each recursion, basically, right? So now let's rewrite list or length to be an APS function, right? Where we're passing an accumulator at each step. So we will again have to change the type. This time we're gonna have a list of A. It'll take a nat also as an argument, and that's the length so far, and output another nat. Okay. Length of nil, ACC, should be what? Yeah, it's going to be the accumulator again. So notice a pattern there. When we're using APS style, we're usually going to put the accumulator for your base case. For whenever you hit empty list or say 0 with the numbers, you'll have just ACC. And now the cons case is the more interesting of the two, of course. So we have cons x's, ACC, and what should this be? Yeah, so Brian says ACC plus 1S. Can you write it the whole line for me, Brian? Because it needs to be, it should have a recursive call in there too. Yes, that'll be the new value of the accumulator. So I'll write this out. So we're gonna have a recursive call again, so length. And can I make this smaller in a nice way? No, it won't let me. So we'll go to the next line. Length x's, because we have to pass in kind of the rest of the list to deal with. And our ACC, our accumulator, will become successor of ACC. Okay, ACC plus 1, right? So what we effectively done here is moved this S inside the recursive call of length is all we've done here. Now, again, it doesn't really give us any space savings here, nor speed savings. It doesn't actually do anything in the length case. It doesn't do anything for us. But it does exhibit that there's a pattern going on here. So now what other function did I have in mind? Well, it was the plus function.
Can I ask a question before we move on?
Oh yeah, go ahead.
So you're recursively passing in the rest of the list there. You've got length of x's, and then you're taking your accumulator and plus oneing it, and you're like losing your x. You're losing the head of your original list.
Correct.
So that makes sense to me if that x had a value of 1. But if it was the number 5, you've lost 5 and you've only added 1 to your accumulator, right?
It's the length function, not the sum function.
Okay, I misunderstood. I thought we were trying to find a way to sum using the length function.
Oh, no. We're still, yeah, we moved on to just doing the length function in the same style. The sum function was good as it is, as we finished it a minute ago. Does that clear that up?
Yeah, it didn't make sense to me how we were doing this to
Okay.
sum,
Yeah.
and
yes.
we're not.
You be correct. You cannot. Yeah. Especially because we just have a list of A here. So we couldn't do addition with the things inside. So the function I had in mind earlier was actually the plus function. We do this with addition. And this will be our little exercise of the day for class. And I want you guys to kind of get working on this. This shouldn't be too difficult. But remember the other day we wrote plus like this. Yeah, I believe we wrote it like this. X and 0 is equal to X, and then plus X S of Y is equal to S of plus XY. Is that how we wrote it the other day? Are you sure? Positive? Okay. Because if I had us, sometimes I skip ahead and actually have us write it the way I want us for this exercise. I'm going to give you guys a little hint. We don't need to change the type signature for this at all. Okay, we just have to change the definition in the cases a little bit. But can you write this in a similar style where the recursion that we're making in the recursive case, so it always happens on the outside. So like here, it's on the inside of something. Can you make it so it's always on the outside, kind of like up here? Note how up here it's not on the outside. Try that out. Give that a try. And to give you a hint, you'll have to treat something like it's an accumulator. Okay, I'll give you guys a few minutes to do that. While you're doing that, I'm gonna open up that homework. It's fresh in mind. So give that a try, give you a few minutes. It should not take much. I'll give you another hint in a minute or two once you get started. And Linnea, go ahead and check real quick for me. The homework should be open now.
I think we got a pretty useful question in chat about colon versus colon equals.
Yes, I will touch on that in a second. I saw it.
Great, thanks.
It's a little tangential, so yes, I will address that though. Thanks for saying something.
Yeah, of course.
Do we have any ideas? So I'm gonna give another hint. Our first case is gonna stay the same. We're not gonna have to actually change that at all. Does anyone think they have an answer? Or are we stuck? Pretty stuck. People in the room are saying we're pretty stuck. Anyone online got an idea? Okay, so we can actually rewrite this a little bit. So I could rewrite plus as plus. And what happens if I call x ACC instead? Okay, the first case stays the same. Plus, and then I have ACC S of y. Here, can I do anything now? So I write plus, and if this is my accumulator, this argument, well, what can I do to ACC to kind of accumulate that value as we go? I can stick the successor there. Like so. And that gets rid of any extra calls to plus. We have an accumulator now that we then output. Right, and a few people in chat were right on to that. I guess I just didn't give you guys enough time to type. Yeah, so you're basically just taking one stack from one pile and moving it over to the other. But if you think about X as being an accumulator, or you could do this with Y and it's all the same. It's also kind of like an accumulator. Let's just write it in the same style. You could do this also with multiplication. You can do this with a lot of stuff. So good job, chat. You guys were on top of that one. Let's see. So let's see. So now there was a question about some notation. So what is what is colon versus this kind of double colon equals notation? And was that posted somewhere up above today? Oh, yes. Okay. The question is, what's the difference between those two, or when do we use one over the other? Okay. And so what we're doing here, we're kind of actually, when we write with this notation, we're abusing notation a little bit. One comes from more of the math world and one comes from the programming world, which is kind of interesting because this is where they kind of meet. Is if we recall colon, so say A colon T, it's pronounced A has type T, whereas T double colon equals, and then stuff on the right hand side is the definition of a type. So it says when we see a double colons equals, that's saying we're creating a brand new type. It didn't exist before. We're defining it a new data type now. So type T is defined as ... And let me scroll back down. Cool. So these are going to always be used in two very different contexts. One's just when we define new types of data. So like when way back on Monday or Tuesday last week, when we talked about defining the Booleans, we use the double colons equals, right? When we use a single colon, that always means, always means something has a type, okay? They're reversed. They kind of mean different things. This double colons equals comes from mathematics. It just means definitional equality, saying I'm defining this to be this. Whereas the colon is really a statement within our system. It's saying this has this type. It's not asserting it per se, because there's something else about it that says what type it is. So if I said, for instance, 7 is of type list of, say, Booleans, that's just not true. We would say this is ill-typed. But I could always define something with this, right? That's the definition of the type, right? So think about this one as saying something about the type of some term, whereas the other one is really an assertion. It's us telling the system, we're adding this to our system. Okay. And it's actually kind of a meaty question. It's called judgmental equality versus propositional equality. Is when is something true because we just assert it is, we say it is, because, and so it's true because we're telling the system it's true, versus something being true because the system tells us it's true, right? The system allows us to logic our way into that conclusion. It's kind of that trade-off. Does that answer our questions satisfactorily, or do we have some follow-up there? Cool. Looking good so far. If I need to explain more, say something in chat and we'll get to it. A few more questions popped up. Linnea, I will take another look at that and see why the submission isn't open. That could have been something I didn't do right. Next question is, so back up to the plus function. Does the order matter? So would the, let me copy this. Does the order of our arguments matter in the recursive step? So let's duplicate, come down here. Would this second case be the same as equals plus is that what you meant to write? SY ACC, would that be the same? is an open question to the class. You guys are very, very capable of answering this one. Why is it not the same?
It's the same. Well, I guess it's the same thing as we had on the left side, so it is too much.
Yeah, answer that better.
As in, like,
Elaborate more.
The way I see how it usually works, it's like taking one from one of the arguments and putting it on the other each time.
Yeah.
Versus this way, it's like taking one off and then putting it back on the same one.
Right. So we're kind of taking something off and putting it back. We're kind of leaving it alone. If we want to see what this does in practice, let's just do an execution of it. So let's do plus SZ and S and Z. So plus 1, 0 plus 1, right? Or 1 plus 0, I guess, in this case. Which case does this match on? Well, it matches on the first case. Oh, this is a bad example. Okay, let's do it this way instead. So it's 3 and 2. It's 2 and 1. So we hit this second case because this is a successor of something, right? And this tells us, in using this rule, not the one above it, that we have plus SY, which is SZ, and SSZ. Okay. So now let's do this case. Let's simplify further. So I look at the cases, I hit this case again. Now what do I get? Well, it's going to be plus, what's S of Y this time? SSZ. And what's ACC? SZ. So you see how it just kind of cycled through? So we've got, this is a case where we've accidentally bumped ourselves into kind of an infinite recurrence. It seems almost like the logic should work. It doesn't here. Here we're just kind of flipping the arguments every time, and it'll do that forever. So this rule does not work. It also doesn't really keep true the idea of the accumulator, right? So we do, unfortunately here, have to keep the order in mind. And if we think about addition as accumulating a number into one of the positions, it makes a little bit more sense, right? Is we're taking something from one side and accumulating it on the other side. But you don't want to flip the two, otherwise they'll just kind of take one back and forth in a tug of war. That'll never end, right? Does that clear everything up? Maybe, hopefully. If I don't see anything else in chat, I'll assume it did.
Can you move the successor of ACC and then just Y real quick?
Yeah, so let's play with that. So instead, what if we did plus, same case, plus, so what, Y and SACC, or the other way around? So-
Like in the definition.
Yeah.
Plus SACC. and then-
Oh, go the other way. Yeah, so if I did instead plus SACC and Y. So you just did something kind of interesting. Let's change the names of the two, right? So I could then call this X maybe and this ACC, and then do the same thing, right? So you can flip them. The order matters within the definition, but you can choose, when I'm defining this at the beginning, I can choose which one I want to be the accumulator. It doesn't have to be the last one or the first one. It could be either one. But once I've made that pick, it has to be one of them, right? With plus. And we probably shouldn't dive into this too much because you'll never see this exact situation where everything's the same type. That doesn't happen very often. It might come up every now and again, but it's usually with stuff. Usually you're trying to define plus and you just forget how to write it, which happens embarrassingly often for people that should know how to write this. It's like I forget sometimes. I'm like, oh, that's infinite. Take a step back, Jack. Let's work this out, you know? So yeah, so it can be confusing, but just kind of give a job to each of the variables when you're doing this kind of recurrent stuff, and it'll work out most of the time. So like, give it a job. Think about it that way. Other questions? Yes.
So the next step of that is it's just going to be successor of C. C. It's the,
Oh, for the brown?
yeah.
Oh, no. No. So for this case, because that's what we were looking at with the brown. If that makes more sense.
Yeah.
What it would do is it would just flip between these two states. Or no, wait, that's the same state. It would flip between these two states forever. Right?
Yeah.
Yeah. So otherwise it would do what you were saying. If we use the line above it, it would do that. So sweet. Put a little flag here. This is a bad example. To that. Let's see. No more questions in chat. Let's see. Okay, so one more note on some terminology that will come up quite a bit. I want to copy our definition of length through this. When we have the recursive piece of a function, and all it does is call itself, we call that tail recursion. This is terminology we'll need to know. So tail recursion is whenever the right-hand side of a function either terminates or makes a recursive call to itself. What that means is that the first thing you see on the right-hand side is itself, is another recursive call. We see that here with length. We saw that up top with sum. It's the first thing. And it's the only thing, right? Is because that's kind of wrapping everything else up. Is everything else that you see are arguments to that. Okay, so all the computation, if you could think about it another way, all the computation is happening inside the arguments of a recursive call. Okay. And notation note, RHS is right-hand side, LHS, left-hand side. So everyone's seen that shorthand before? I'm actually just kind of curious. You guys have in a math class?
I like middle school.
Middle school? Okay. Yeah, so that's just handy. I'll use RHS and LHS all the time when I'm writing definitions and stuff. Annotate this. Yeah, so note that this is first thing. And now this isn't to say that a tail recursive function can't call other functions. It certainly is allowed to. And there's a way some of you could try and write multiply on the homework where you could write it in a tail recursive style and still use plus. But that's going to happen inside one of the recursive arguments. I believe that works for multiply. Should work for multiply. So something to note, you're allowed to call functions, kind of like how we added a successor here. We're allowed to do stuff to the arguments, but we want to make sure that the length is on the outside. Okay. Questions about that terminology? Is anyone kind of confused? Any elaboration necessary? Why do we like tail recursion? Because I really like it. It's a great way to write functions.
Pretty easily tell if it's going to terminate.
Yeah, it's really easy to tell if stuff's going to terminate for the most part, not always, but usually it'll be a little easier to tell if something's going to terminate. It's also really easy to do those evaluations. So something I didn't necessarily say earlier is that just because we use accumulator passing style up above, right? So this APS guy, APS is a way of getting us tail recursive functions. You can certainly use it, I think, in a way that doesn't give you tail recursive functions. There might, yeah, I guess you can definitely kind of use both techniques. But usually the goal of APS is to give us tail recursive functions because they're so efficient. They're a lot easier to read and reason about often. So I'll write that down. APS is a tool or technique for getting tail recursive functions. From non-tail recursive functions. Cool. Sweet. Let's see. Got up to there. That pretty much wraps up the tail recursive stuff. So I'm going to finish this off today with a little bit of an intro to tomorrow's class. So let me think about the example I want to do here, though. Yeah, so first let's write a function, and you guys all know how to write this function already, probably. We've done something similar. Can we write a function that adds 5 to every number in a list? Can we do that? So exercise time. We'll call this function add5, not to be confused with the add5 we used earlier I'd say in the semester last week. It was last week. What type is this going to have? It takes what? Right, a list of natural numbers, list of n. And what does it return? A list of natural numbers. Right on. So now I give it the most general case. We can kind of skip that. As usual, you can kind of skip that case until later. And we'll introduce a nil case. And a cons case. Okay. Now help me fill out these cases. I'll give you guys a couple minutes to try and work this function out. I don't want to rush you. we've got the time. So, yeah, those of you online and in person, try and write the rest of this function. That adds 5 to every element in the list. Does anyone have at least the nil case for me? It depends.
Yeah, I mean the way I did it, I tried to see if I could like add an accumulator type of list.
Don't do that. Here, this function should not have an accumulator.
It probably should be no.
Okay, just nil. I like that. So we'll just have nil here. We could add an accumulator to this function. We will not, though. Now I teach you how to use a tool and then immediately take it away, right? But we'll see how to write this with an accumulator probably next week. Okay, now does anybody? Oh, it's add 5. Add 5.
Instead of returning nil, could you tell it to return the same list that it received?
You could. Where are you going with that, though?
The reason I thought of that was because if it's seeing nil, then it's just been passed an empty list.
Right.
And so when I was thinking return nil, I don't know if when it wants to return nil, if it's going to recognize that this is an empty list or if this is just some kind of void, nil, null, something else, like not applicable. So I was thinking just return the
Oh, yeah.
list.
So remember, we don't have null. Null doesn't exist here. We're definitely getting a list. So nil just means the empty list here. So Arthur has an answer for us. So he says our recursive case could be, let's see, would be cons of I need to break this out on a new line though. So it'd be cons of x plus 5. You wrote it out in the longhand, which is good. I mean, the longhand is correct. And then make the recursive call here of add 5 x's on the far side. How do we like that? Does that get the job done, do we think? It does. Okay. Now what if I wanted to say So a new function for you guys to try and write. Let's do, apply the not function to every element in a list of Booleans. So apply not to every element in a list of bool. Okay, what's the type of this guy? We'll call this function all not. What should the type of this be? Yeah, so list of bool to list of bool. Okay, again, I'll have two cases, one for nil. And one for cons. Now you guys take a second to try and write this function. Joseph, to answer your question, sort of, it can, the result can. Oh yes, yeah, for that purpose, those are the same thing. You could also write it as 5 successors. Okay, does anyone have a solution for me? You think you got it? Maybe.
Is it cons of not x and then all not x's?
I like it. Okay, I think I parsed that right. So you said, say it again.
Cons of not x.
Use a smaller marker. Cons of
Not x.
not x,
And then outside parentheses, all not x's.
and then the recursive call, right?
Yeah.
Does that look right? How do we like this? Look good? Any objections? Yeah, some in chat are saying the same thing. I like it. Yes.
Well, if x was true, if x was already false,
Yes.
just be changing it to true.
Correct. We're applying the not function. So not false. We're not making everything false. Instead, we're negating everything. Right. So we're just applying that function that we wrote last week. Right. Cool. Sweet. What do we do for the nil case? Just nil. Cool. Do we notice a pattern between these functions? Can anyone spot the pattern?
In the last bit of each of them, there's like, we're trying to do not in the second case, and we're trying to add 5 in the first case. And so that's in both of them right after the cons in that last line. And that's like the function that we're trying to do in the list.
Okay, so we're trying to do something to every element of the list, right?
Yeah.
Yeah, so let's write that down as an observation. We're trying to apply a function to each element of a list. That's our pattern, right? Kind of summed up in English. So there's a pattern here. When we see patterns, we like to abstract, right? We don't want to reuse, like these kind of capture some of the same stuff, right? There's a pattern kind of in the definitions. Nil is nil, and then the recursive case applies some function to the inner element, right? Do we think we could abstract that? How do we do that?
You want to strip off the first element, apply the function, and then do a tail recursion on remaining elements.
Yeah, just a recursion here. We're not doing any tail recursion with this yet, but everything else you said was right. So we're, strip off front element, apply the function to that element, and then basically repeat and combine kind of the whole rest of the list, that recursive step, right? How do we write this? Could we write this abstractly as a function, maybe? Because we can certainly describe this in English, and we can maybe see there's a pattern in the way we wrote this in the two functions. Could we write this as a function?
Maybe so like what we did with list of A.
Yeah.
Like iterative of like X would be a function of A, and then you have like
Oh, okay.
two space. I don't know, yes, but two spaces, and then that's two variables. One of them being a function that being
Oh.
not X.
Oh. Points. I can't say anyone's kind of gotten that before. And Brian coming in clutch. He's also say we're going to implement map. Yeah, we need to take in a function and accumulate on it, is what Brian says. Right on. Between the two, you guys are knocking this out of the park. So because we're running up on time, we're going to do this first thing tomorrow. Is we're going to define a function called map. Okay, and map is going to be this really cool function that takes a function from A to B as an argument. Okay, that's why we put parentheses around it, is it's taking a function as an argument. And, why can't a function be an argument? Certainly it can, why not? And it'll take that as an argument, and it'll take a list of A, and it will give us a list of B. Okay, but we will pick up with the definition of that tomorrow, and we'll work that out as a class. So otherwise, have a good evening, everybody. I will fix the homework submission after I leave here. So expect that to be up in the next hour or so. Same with the quiz. Quiz will be up in the next hour or so. That's all I got for you.
Thank you.